how to remember the periodic properties, gradation of the periodic properties in a modern periodic table. A small trick I shared with you. So I wanted to explain that briefly. So one by one property we'll see. The first property we see here, atomic size. But before going to that, just I want to compare these all properties together so that we can remember that easily. So here I am taking two atoms, two elements I am taking here. So in this one, if you see, atomic size of this element, if you take, means the first element I am saying this as A, the second element I am saying it as B. So atomic size of this element A is very larger compared with the B. So what happens here, atomic size means nothing but from the center of the nucleus to the outermost electron, whatever the distance is there, that distance we are calling it as atomic size. Distance between the center of the nucleus to the outermost electron is nothing but the atomic size. So atomic size of A is greater compared with the atomic size of B. Right. So because of this higher atomic size of this element A, it wants to lose the electron very easily. Element A wants to lose the electron very easily. The tendency of any element to lose the electron is nothing but electropositivity. Electropositivity. Electropositivity of this element A is greater because the size is greater. Tendency is more because the size is more. It wants to lose that electron very easily. So atomic size of this element is more, electropositivity also more. So whenever it is losing the electron, it undergoes oxidation. Whenever any element or any substance, if it undergoes oxidation on its own, if it is undergoing oxidation, it reduces the other element or the other substance. So we can say that reducing property is more for this. Reducing property of this element is greater. As it is undergoing the oxidation, it reduces the other element. Right? So atomic size is more, electropositivity more, reducing property more for A. Now coming to B. B is smaller compared with A. So what we can say here, atomic size of this element, atomic size is less compared with A. And as it is very smaller, it cannot lose the electron easily. Instead of that, it can attract the outer electron. Outer electron in the sense, if any electron is there outside of the outer shell, if any electron is there, it has a tendency to attract that electron towards it. Here we have a property known as electronegativity. The property or the tendency to attract the electron. Clearly, if you want to say, the tendency of attracting the electron pair, shared electron pair towards itself after formation of the covalent bond. If any element is attracting electron pair towards itself, that property we can call it as electronegativity. So it wants to attract the electron. Tendency to attract the electron is nothing but electronegativity. So electronegativity of this element B is greater. Electronegativity of this element B is greater. Now, as it is attracting the electron, it is undergoing the reduction. This B element undergoing the reduction. So, as it is undergoing the reduction, it oxidizes the other element. It oxidizes the other substance. So, what property is more for this? Oxidizing property is more. Oxidizing property is more. Right? So, just compare A and B here again. Size is more. Because size is more, electropositivity will be more, and reducing property also will be more. Coming to this B element, as the size is less, it can attract the electron, electronegativity is more, and oxidizing property also is more. Means if you want to say electronegativity of A is less than B, electropositivity of A greater than B, reducing property of A greater than B, oxidizing property of A less than B. Same like that for B also, atomic size is less, electronegativity is more, electropositivity is less, reducing property is less, oxidizing property is more. Like that we can compare two elements. So this clarity, if it is there, we can understand all the other properties also very easily. Right? Now let us see about atomic size, how it is changing in the group and and also in the period. Now, with some examples, like one group and also one period we'll take, and we'll see how it is changing in the period and also in the group, right? So, atomic size in that trick, what I said for you, in that trick you have seen already that atomic size increases from top to bottom in a group, and in a period from left to right it decreases. So, based on that, if you want to learn, just to take the first group: hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. So in these all elements, if you observe, first period element hydrogen, atomic number 1, so only one shell is present in that. Last shell it has only one electron. Coming to lithium, atomic number is 3, 1s2, 2s1 will write. So here it has 2 shells. I am not drawing all the electrons here, just outermost electron, and number of shells only I want to show. Then coming to sodium, as it is present in the third period, 3 shells are present along with the nucleus. In potassium, as it is present in fourth shell, it has 4 shells. Fourth period it is there, that is why 4 shells are present. Rubidium is present in fifth period, so 5 shells are present for that. 5 shells are there. Outermost electron is present in the outermost shell, means valence shell. Next, coming to cesium, it is present in 6th period, 6 shells are there. Francium is present in 7th period, so 7 shells will be present. So from top to bottom, if you observe, number of shells are increasing. As number of shells are increasing, size also increases. Distance between the center of the nucleus to the outermost electron increases. So because of that, we can say clearly that size increases, atomic size increases from top to bottom. Here exactly, if you want to say the word atomic radius, we have to say atomic size means total atom size will come, but many of the questions also they are giving like that. So atomic radius, actual word is atomic radius. So atomic size from top to bottom it increases, right? Same like that, if you want to see about a period, how it changes in a period. So here if you see, number of protons are increasing, number of electrons are increasing. That word we are not discussing here. Only shells we are seeing, because the number of shells are increasing, size also increasing. But when you want to learn about the period, the property, how it changes in the period, that if you want to see, here we have to consider the protons and also electrons, right? So that we will see, we'll take the second period as an example, because first period we have only 2 elements in the modern periodic table, hydrogen and helium. So we can't compare the periodic property there. So let us go to the second period. So second period elements, if you see, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, right? Here I am not taking neon, right? Why? Because atomic size or atomic radius of the inert gases, if you want to learn, we have to take the van der Waals radius. Van der Waals radius. Here we have the atomic radius again, different types like metallic radius, covalent radius, van der Waals radius, right? So as inert gases will not participate in the chemical bonds, inert gases are unable to participate in the chemical bond. That is why what happens, they are not, as they are unable to participate in the chemical bond, covalent radius or metallic radius we are unable to calculate exactly. So that is why we will go for van der Waals radius. So like that, if you compare again, van der Waals radius will be greater compared to the remaining radii. So that is why I am not taking here inert gas. Remaining all will check it here. So lithium to fluorine. Lithium to fluorine I want to compare. Lithium, number of electrons 3, number of protons also 3, right? Here 4, 5, 6, 7, 8, 9. But as generally we think that as the number of electrons, protons are increasing, so size also will increase. But what is happening here? All are present in second period only. All of the elements are present in second period. So how many shells will be there? 2 shells will be there. Everywhere, lithium to neon, lithium to fluorine we are taking here. From lithium to fluorine, every element is having the only 2 shells. So that is what we will think, as 2 shells are present, as we have discussed here, number of shells. Based on the number of shells, we are saying that size is increasing. So based on that, like that only if you consider, we may be thinking like size of these all elements will be similar. But what is happening here? Number of electrons and also number of protons are increasing. So because of that, what happens here? The protons are able to attract that electrons. The nucleus is going to attract that electrons towards it. So because of that, what happens from left to right, size decreases. Atomic size from left to right decreases. In a period, atomic size decreases from left to right. Same like that, in a group from top to bottom, atomic size increases. Right? Now, coming to the second property. Second property, ionization energy. Ionization energy. So here, ionization energy, actually it is affected by different factors. In a group, if you want to learn, we are going to see only atomic size, how it is affecting. So based on that only we can discuss here. But coming to period, how it changes in the period, if you want to learn, we have to see the remaining all properties also. Right? So here, ionization energy in a group from top to bottom, what happens? Size is more. If any element has more size, it can lose the electron very easily. It can lose the electron very easily. Tendency of losing the electron is more for any element when the size is more. So here what happens, as the size is increasing from top to bottom, this ionization energy will decrease. We are saying that it is able to lose the electron very easily. If it is able to lose the electron very easily, no need to use more energy to pull out the electron. That is why from top to bottom, ionization energy decreases. If any element is very larger, this ionization energy value will be very less further. So like that, from in a group from top to bottom, if you observe, the ionization energy value is going to decrease. Here we are considering only atomic size. But when you go for period, here period, if you want to see, as I said earlier, we are saying actually one word, there is no order for the ionization energy. Why we are saying like that? There is no order. So let us take the same elements. Lithium is there here. Now here, if you want to see the ionization energy, how it is having the gradation of this ionization energy in a period, here we have to see the remaining factors also. What are those factors? I'll say here. So first let us say lithium is there here. Here we are going to write electronic configuration 1s2 2s1. We wanted to remove the electron from 2s. Okay. Then coming to beryllium 1s2 2s2. We wanted to remove the electron from 2s also. Here also 2s only compared with the lithium. Beryllium size is less. So that is why we have to apply more amount of energy on beryllium. So beryllium is greater than lithium. Means ionization energy of beryllium is greater than lithium. Now coming to boron. What is happening in boron? If you see here, boron electron configuration 1s2, 2s2, 2p1, we are going to write atomic number is 5. So that is why we will write here 1s2, 2s2, 2p1. So here you want to remove the electron from 2p. You wanted to remove the electron from 2p. Now here if you see 2s, the shape is spherical. Here the shape is dumbbell. The p shape is dumbbell shape. So what happens here, this p orbital, that means the electron which is present in the p orbital is not attracted more towards the nucleus. Now to understand this clearly, just to take two persons, one person very fat and one person very lean. Right. So these two persons, if they want to enter into a market which is means a crowdy area like that it is there, lean person can go very easily, the fat person cannot go that much easily. Like that here also, this dumbbell shape is there, it cannot, means the electron which is present in the p orbital cannot penetrate towards the nucleus. It is not attracted more towards the nucleus. When it is present in s orbital, it is attracted more towards the nucleus. That is why it is easy to remove the electron from p orbital compared with the s orbital. That is why what happens here again, compared with the beryllium, boron has less amount of energy. Ionization energy of boron is less compared with the beryllium. Now coming to the next element, what is that? Carbon. So in this carbon, if you see again, what is the electron configuration? 1s2, 2s2, 2p2. Now again the same orbital, 2p only. So what happens here? Generally what we have, from left to right increases. So the same thing we are going to write, as size is less for carbon compared with the boron. It is not that much easy to remove the electron. That is why it is greater for carbon compared with the boron. Now coming to next element, nitrogen. Here the electron configuration of nitrogen we are going to write 1s2, 2s2, 2p3. Now, if you compare these two, both are present in p orbitals, right? But one thing we have to see here, nitrogen has half-filled electronic configuration. Half-filled electronic configuration gives some stability for the element. That is why it is not easy to remove this electron from nitrogen. Nitrogen will not agree if anybody wants to take away one electron from it. Compared with the carbon, nitrogen has here half-filled electron configuration is there. That is why it is greater for, means it is not that much easy to remove the electron. So that is why it is greater for nitrogen. Now going to oxygen. Here in oxygen again we have 1s2, 2s2, 2p4. Total number of electrons are 8. 1s2, 2s2, 2p4. Now nitrogen and oxygen, if you compare, nitrogen has half-filled electronic configuration. Oxygen does not have the half-filled electronic configuration. 1s2, 2s2, 2p4 we are writing. So that is why what happens here, ionization energy of nitrogen is greater compared with the oxygen. Actually it is increasing from left to right. But here and there some exceptional cases are also there. That is why we write no order for ionization energy. Next, oxygen and fluorine if you compare. Oxygen and fluorine if you compare. Oxygen will be greater compared with the fluorine. Because here electron configuration 1s2, 2s2, 2p5. Not only electron configuration here, the size of this fluorine also is very smaller. It is a highly electronegative element. Highly electronegative element compared with all the remaining. Means it does not want to lose its electron. That is why for oxygen it is for fluorine it is greater compared with the oxygen. Right? Then again neon means inert gas. It does not want to lose the electron. Fully filled electron configuration is there. Octet configuration is there again. That is why it is greater for neon compared with the fluorine. Like that, from left to right in a period, if you see, there is no particular order for this ionization.